Now, so we are going to discuss types of forces. Okay. Now in today's class, we are going to discuss types of forces. Depending upon their origin, and system wise and nature, depending upon nature, and there is another one: origin, system wise, nature wise, and fourth one is frame of reference. So depending upon these forces, origin, that means the origin of the force. Based on that, we are classified this origin of the forces. We are classified into two types. The first one is contact forces. Contact forces, and second one is non-contact forces. Non-contact means, or we can also call it as field forces. Okay, and the system wise. So the system wise we are classified into two types: external forces, external force, and internal forces. And nature, depending upon nature, we are classified into two types: conservative and non-conservative. Okay, and depending upon frame of reference, we have two forces: real forces and pseudo forces. So this is the basic classification of forces. Okay, so we will see one by one. Okay, so first I will briefly explain this regarding these forces, then we will go one by one. Okay, in dynamics we are mainly concentrated this contact forces and non-contact forces. What is this contact forces? The origin of the force is because of contact, one body contact with the other. So due to this contact, this force arises. Due to contact, one body exerts a force on one another. So such forces we can call it as, this is because of physical contact. So non-contact field forces, there is no physical contact between the forces. Suppose example, this contact forces examples is normal reaction, frictional force, tension. These are the main forces we are going to study. First I will write tension, then I will write friction. Before going to friction, normal reaction, tension, spring force and the frictional force. These are the few examples for Contact forces. What are the examples for contact forces? Normal reaction, tension force, spring force, frictional force. And the non-contact forces. Non-contact forces is there is no physical contact between the bodies. Example, Earth attracts the due to gravitational force, the satellites revolves around the Earth. Apple falls down because of gravitational force. There is no contact between apple that falls on the earth between the earth. Still, it is pulling down. So, these are the non-contact forces. Examples are gravitational force, and electromagnetic force, electrostatic force, magnetic forces, force between two magnets, magnetic forces, and so these are the non-contact forces: magnetic forces, gravitational force, electrostatic force, and magnetic forces. These are the non-contact forces. Examples. And the system-wise. The system-wise is we are classified into system. What is the system here? The bodies, the objects which may be connected together. Those objects, if two objects are connected by a string or spring, then those two objects we can call it as a system. In that system, two objects are connected with the help of a string or spring by means of a pulley or some other. So that way constitutes a system. So the system consists of many objects which may connected together with the help of strings or springs. That constitutes a system. So if you want, here the objects we will treat as a rigid bodies. That means its shape, it won't change by applying the force. Okay, so here we will treat objects as a rigid bodies, and the system we consider as a external. Depending upon the system, we have to classify it as external and internal. So if you consider two objects as a system, two objects are connected by a spring. You push that one, so that pushing is an external force. In that spring, there is internal forces, that is spring force. So that we will discuss in detail next. So external forces and internal forces. Okay, that is depending upon the system. So that means what forces you are consider, which object you have to consider. Suppose if you want in the system, it consists of many objects. Suppose you want to study the motion of a object, then other objects will become external to it. Okay, so this depending upon external forces and internal forces. And the next one is nature of the forces. These are the conservative forces and non-conservative forces. So conservative forces may be gravitational force. It is conservative in nature. Gravitational force and electrostatic force. They are conservative in nature. Non-conservative forces means frictional force, viscous force, frictional force and viscous force. That is, they are opposing forces. Okay, friction is a opposing force. So these are non-conservative in nature, conservative forces. Okay, what is conservative, non-conservative, we will see one by one. Okay, the frame of reference. So these are the examples for this. Okay, conservative and non-conservative. Real forces and pseudo forces. That depends upon frame of reference. I said frame of reference is a reference to, we need generally a Cartesian coordinate system we can consider as a frame of reference which is fixed. To study the motion of the object, we need the frame of reference. So based on that frame of reference may be at rest or may be moving with uniform speed, or it may be accelerated. Okay, so depending upon that frame of reference, we are classified into two types of forces, real forces and pseudo forces. Now, we are going to study in this dynamics, we are going to study one by one. Okay. Now, first we are explaining this contact forces. Okay. Now, these contact forces. So, we are going to deal about contact forces. These contact forces, the first one is normal reaction. Normal reaction. So, it is represented with N or R. We can represent either letter. Okay. So, this contact force, it arises because of the contact between the two bodies. Now, let us see these examples. A block is placed on a surface. So, let it be a block. It is placed on a surface. What is this? Horizontal surface. Horizontal surface. So, this block, there is a gravitational force acting on that block. What is that gravitational force? Nothing but weight of the block. So, that weight of the block acts from, we are assumed that this entire weight acts from center of gravity. Okay. That center of gravity, we are assumed that for regular shaped bodies, it is at its center. Okay. So, that is weight of the body, which is acts vertically downwards. So, the second one is this surface, horizontal surface, in turn exert a force on the object which is vertically up. So, that is normal to the surface. Hence, it is called normal reaction. So, what is the force exerted by this here? What is the force exerted by? Force exerted by the force exerted by the block on the surface. Can you say it is force exerted by the block on the surface is W. That is nothing but weight of the block. Weight of the block we have it written as mg. Okay. So, W is equal to mg, where m is mass of the block. What is m here? Mass of the block. Mass of the block. What is g? Acceleration due to gravity. Acceleration due to gravity. Okay. Then this is the force. Next, if force exerted by the surface on the block, how much? It is N. That is called normal reaction. This is the surface, horizontal surface. It exerts on the force on the block vertically up. So, this is the representation of forces. So, this N, it will forms action reaction pair here according to Newton's third law. Okay. So, this weight, these forces arise because of contact. This block is contact with the horizontal surface. So, these two forms action reaction pair. So, under equilibrium, since the block is at rest, we can write it as N is equal to mg. Since the block is at rest, we can say that on the system, the net force acting on the block is here N is equal to mg. Since the block is at rest, the net force acting on the block will be 0 only, because you consider these are the two forces acting on the block. What are the forces acting on the block? Normal reaction and weight. how they are represented from center. Okay, so we are assumed that this entire weight of the body is supposed to be acts from its center, and in turn this weight acts from center normal reaction. Okay, this is one example for normal reaction. Okay, the second example is, see, suppose there is a inclined plane. A block is at rest on the surface. Let theta be the angle of inclination. Okay, what is this? Inclined plane. Okay, so what is theta here? Angle of inclination. What is angle of inclination? The angle made by the plane with the horizontal is called angle of inclination. Now this weight of the blocks acts vertically down. Gravitational force acts always vertically down. Now in turn this weight is resolved into components. This component this is mg. Okay, this angle is theta. This is 90 because this is vertical and horizontal. This is theta, then this angle becomes 90 minus theta. If this is 90 minus theta, this angle becomes theta. So this component becomes mg cos theta, and this component is mg sin theta. So the component of weight acts along the plane down is mg sin theta, which is responsible causing this block moves down. This component of gravitational force is responsible for the cause of motion of this block, because the block is, when you keep a block on the smooth inclined plane, it slides down because of this force mg sin theta. So here on the surface the block exerts certain force on the surface. In turn this surface exerts in turn normal to the surface. That is called normal reaction, N. So in this case normal reaction, so what is the force? Force exerted by the block on the inclined plane on the surface. Can you say force exerted by the block on the surface? It is mg cos theta. Okay, so what is the force exerted by the block? This is by the block on the surface. By the surface on the block. Can you say it is N? It is N. This N is called normal reaction. These two forms action reaction pair. So here we, under equilibrium, we can say that N is equal to mg cos theta. Okay, so this is another example for normal reaction, and I will explain few more examples. Suppose there is a ladder. Ladder is placed like this. Ladder. What is this? Ladder. This is ladder. These are walls. This is a horizontal wall. This is a vertical wall. Now this ladder is in contact with this floor. This is a floor. This is a wall. Sorry. This is a floor. This is a wall. Vertical wall. Now this ladder is in contact, physical contact with the floor and wall. So there are two normal reactions here. The number of normal reactions in the problems in the given situation, in the given instant, is equal to number of contacts. Suppose the body contacted to two different places, then there will be two normal reactions. If there are at three places, then there will be three contact forces. And here this normal reaction acts normal to the surface here like this. So this normal reaction, let it be N1. Okay, this normal reaction, let it be N2. Okay, it will act like this, N2. Okay, so these are the normal reactions, acts on this body. So what is N2? Can you define what is the weight of the block? Acts from center of gravity. So these are the forces acting on this ladder. Now, what is N1? Can you say? It is a force exerted by the ladder on the wall, on the vertical wall. Can you say force exerted by the wall on the ladder will be remains the same, that is in this direction. So action reaction here fair. Force exerted by this ladder on the wall is N1, force exerted by this wall on the ladder is N1. Exactly opposite, same magnitude. So what is N2? Can you say force exerted by the ladder on the floor? On the floor. Here how many normal reactions? 2 normal reactions. Can you say the force exerted by the floor on the ladder? Can you say? Answer is N2. Okay, both are same. Force exerted by the ladder on the floor, action. Force exerted by the floor on the ladder is reaction. So both are equal and opposite in directions. This is another example. Okay, I will give one more example to understand this. Normal reaction. Suppose there is a spherical sphere like this, just placed. This is a sphere. Okay, this is a floor. This is a wall. Okay, a sphere is just touch the wall. Just touch the wall. That means this sphere, it does not exert any force on the wall. So the entire weight of the sphere acts vertically downwards. Weight. So it's exert a normal reaction in this direction. So here it is contact with the wall. But here normal reaction is, there is no normal reaction here. The number of contacts, if normal reaction exists or may not exist. When it will exist, when it will not exist. So if it exerts certain force on the wall, then it exerts equal amount of force by the wall on the object. Suppose this object sphere does not exert any force on the wall. So here there is no normal reaction. So this force exerted by the sphere on the wall is 0. So then what is force exerted by the wall on the sphere? Can you say? It is also 0. So what is the force exerted by the sphere on the floor is weight. W is equal to mg. What is the force exerted by the floor on the sphere? Can you say? It is N is equal to mg. It is M. That is equal to mg. Okay. So since the sphere is in equilibrium, we can write N is equal to mg. Clear? So these are the few examples which enables us to understand what is normal reaction. Clear? This arises because of contact forces. Because of contact, the physical contact, it arises. That is the origin of this force. According to Newton's third law, if a body exerts a force on another one, another body exerts same amount of force on the first body. Okay. The second one is tension force. This is contact forces. The contact forces. We are discussing contact forces. Contact forces we are discussing. Okay. And another example is tension. Tension force, or simply we can call it as tension. Okay. So this tension arises in the strings when objects are connected with the help of strings or springs, or with the help of pulleys. Objects, when they are connected with the help of strings, with the flexible strings. Suppose this is a object. Okay, this object is connected with the help of string. Here it is tight. That string. What is this? A string. String. What is this? Block. This is a two object system. Okay. So the point now. So when the string is loose, so when you pull this string with the help of hand, so pulling force, you are pulling this string with the help of your hand. So this hand pulls the string. Okay. Then the string, if you are not pulling, the string is loose. There is no tension in the string. Once you start pulling the string, then the string becomes tight. So that tension arises in the string. Such forces in this string are called tension forces. So this tension is always a pulling force. Suppose your hand is here, you are pulling the string. So from Newton's third law, this string pulls the hand with the same force. Pulling force, let it be F. The tension in the string, let it be T. So when you are pulling the string with the help of hand with a force F, then the string exerts same amount of force on the hand. String becomes tight. That is tension in the string. Now this string, what it does in turn, it pulls the block in this direction. So that is the tension in the string. And this block in turn exerts a force on the pulls this string. So that is action-reaction pair. Here you consider this a system. So here the system consists of block, hand, string. There are three things here. So what is the tension in the string? This tension is a tension force arises in the strings or strings, which is when it is tight, when the string is tight. So what is the tension force? The force arises in the strings. In these strings, when they are pulled, okay. So force arises in the string when they are pulled, when the string is pulled. So this force is called a tension. So this tension is always a pulling force. Never push. Okay. So this tension is also a force which arises in the string. when the string is loose, when the string is loose, that means no pulling force. Loose means no pulling force. No pulling force. So when the string is loose, what is the tension in the string? It is represented with letter T. Tension in the string. Can you say? Tension in the string is 0. Okay? Tension in the string is 0. When the string is loose, there is no tension. Here, now see, this string arises because of pulleys also. See, there is a pulley. What is a pulley? Pulley is a wheel which is fixed based on this fixed axis of rotation. So it is fixed at its center. It is a wheel. So that wheel rotates about this axis passing through center, okay, without any friction. So if a string is passed over the pulley, okay, so these are the objects. How many objects I assumed? 2 objects, A and B. How these 2 objects are connected? With the help of string. These 2 objects are connected. So this is string. This is a string. This is pulley. So where is the string? That string is passed over the pulley. So let it be that pulley is fixed to the floor, to the roof. What is this? Roof. Fixed roof. That is fixed roof. Okay? It is connected. So that pulley is connected like this. Okay? Now, here what are the forces acting on this system? I will consider these objects, pulley, string is as a system. That system consists of many objects here. Okay? So what are the forces acting on this object, on this system? So here what are the forces acting on these objects? Okay? This gravitational force acts on this mg, and when gravitational force, if mass of B is greater than A, so ultimately the body moves down, this body block B moves down, this block moves up. Okay? So when the string is tight, the tension will be produced in the string. That tension is on either side of the string. Either side of the pulley will remain the same, provided this pulley is ideal pulley. So I consider this pulley as ideal. What is the ideal pulley? So it has certain characteristics. Okay? Yeah. So let us study this forces. What are the forces acting on this block A? So here gravitational force mg, mass of B mg, and the mass of A, ma, is also down, ma into g, and the tension is acting up. And here T is the tension on the string. Here I want to explain what is the ideal pulley. What is ideal pulley? Ideal pulley is, which is rotating, it is a frictionless pulley, frictionless, massless pulley. Okay? Massless pulley, and rotates about a fixed axis or mobile axis, about a axis without any friction. and such a pulleys we can call it as ideal pulleys. If ideal pulley, the tension in the string, since there is no friction, tension on either side of the string, either side of the pulley is same. Either side of the pulley is same. Okay, same. The tension on either side of the pulley is the same. Tension in the string on either side. I will write like this. Tension in the string, because tension arises in the string only, on the either side of the pulley is the same. And our assumption is string is this string which we are using to connect these two objects. That string is a flexible, and the string is, it should possess inextensible, that means its length constant, it does not extend on the load, with the load, so that is called inextensible, and torsionless. These are the assumptions. If these assumptions are satisfied, then such a pulleys we are using are called ideal pulleys. Why we are using these pulleys? To change the direction of force. Why pulleys are using? To change the direction of tension force. We are using such pulleys. Okay. Now can you represent this weight of the forces acting on this? So what are the forces acting on this system? So mass mg, tension up. Okay. And this is the tension on either side of the string is same. Because we are assumed that it is ideal. Now what are the, so here we have to draw FBDs. So what is FBDs? Okay. The next one is FBDs, free body diagrams. Free body diagrams. We can call it as FBD. What is FBD? Free body diagrams. These diagrams helps us in solving when to apply this Newton's laws of motion. Helps us. What is the free body diagram? In the system, the system consists of many objects. Here what are the objects? A and B. These two objects are connected with the help of a string. Okay. The system consists of many objects. Suppose you want to study the motion of a object, either A or B. Then you isolate that one. Isolate that body. Imagine which is at rest. Then represent the forces acting on them. Okay. So you treat that body as a point mass, irrespective of its size and shape. You treat body as a point mass, and represents the forces acting on the body, which you are going to apply Newton's laws of motion. Okay. So the free body diagram issue. First you isolate the system on which Newton's laws are applied. Newton's laws are going to apply. Okay. Isolate the system on the Newton's. Isolate the system on which Newton's laws are going to apply, and treat body as point mass, and isolate. Isolate means separate them, separate it from the system, separate it, isolate. Treat body as a point mass irrespective of its size and shape, and represents the forces, acting on the body. Okay, represents the forces acting on the body, whether it is known or unknown, whether known forces or unknown forces, known or unknown forces, known or unknown forces. Represents the forces acting on the body with directions, because force is a vector quantity with directions. Okay, these diagrams are, and apply Newton's second law. Apply Newton's second law. To study motion, to study its motion. Okay, so such things we have to follow to draw these FBD diagrams. Okay, so now you try to draw FBD diagrams in this example. So I want to draw this FBD of A. What are the forces acting on it? What is forces acting on it? A, down, its weight is mg, down, and the tension acts up. So this body A having the mass, m, you treat as a point mass. Okay, first you isolate the system on which Newton's laws are going to apply. Identify the system on which Newton's laws are going to apply. Identify the system on which Newton's laws are going to apply. So identify this body A. I isolated them, and I treat it as a point mass. Isolated it from the system. Okay, this body A is isolated from the system, and represents the forces acting on it. So T and MAG, down. So this is the FBD of A. Suppose it is moving up with acceleration A. Okay, so that is a representation of this. Suppose you want to write the equations of motion. Okay, suppose you want to write the equations of motion here. So what you will get? What is the equations of motion? The resultant force is, so equations of motion, sorry, not equations of motion, apply Newton's second law. Apply second law. So what is second law? F is equal to ma. So what are the forces acting on the object? Tension and mg. So ultimately the body moves in which direction? Upwards. So the T will be greater. So we can write it as T minus mag is equal to ma, mass of A into A, acceleration. So this is the equation. Okay, and the second one is, I want to draw FBD of B. Okay, FBD of B. Okay, So I will take this one as M1. This I take it as M2. M2 greater than M1. Okay. So here I will write this is M1. This is M1. Okay. I assumed this one as M1 for simplicity. So this FBD is, the block B is having the mass M2. What are the forces acting on it? Its weight M2G down and the tension up. So this tension is always a pulling force. Now ultimately the block moves in which direction? Down. So write the equations of motion. I represent this is the FBD of this. Okay. Now write this equations of motion for this. What is the equations of motion here? M2G minus T is equal to M2A. Why I have written M2G minus T here? Why I have written T minus M1G is equal to M1A here? Do you understand? The body moves in the direction of resultant force. Here I assumed that M2 greater than M1. So this is greater force. So greater mass, it moves down because of gravity. So since it is moving down, we have to write M2G is greater than T. So we have to write resultant force. These two are opposite directions. So what is the resultant force? M2G minus T is equal to, it moves with what acceleration? M2A. So this is nothing but Newton's second law. Clear? How I am applying Newton's second law? You have to learn by drawing these FVD diagrams. So you consider the forces in which direction the body moves. Okay, the body moves in this direction, vertical direction. So you consider the forces only in vertical direction. Clear? So I got this. Now by solving these two equations, so this is equation 1, this is equation 2. You will get solving the equations, solve equations 1, 2. We get acceleration and tension in the string. Tension in the string. Okay? We get. See, this acceleration, this is one method. Solving the equations 1 and 2, you will get the acceleration and tension in the string. That is one method. The second method is, directly we can write acceleration. You can treat this one as a system. So the external forces acting on the system is only gravitational force. Here tension is an internal force. According to Newton's third law, the block B pulls the A with a force T. The block A pulls the B with the same force T. That is internal to the system. The external force is gravitational force. It is pulling down. So from that we apply the acceleration of the system is net pulling force by net mass. So this is also seems to be Newton's second law. F external is equal to acceleration is equal to A is equal to F external by mass. So this is also Newton's second law. Okay. So by what is the acceleration of the system? Net pulling force is, this is greater M2G. This is M1G. It is moving down. It is up. So it is greater. So M1G is also acting down, but it is greater. So it is moving down. What is the resultant force on the system? M2G. M2G minus M1G by net mass is M1 plus M2. Okay. So that is M2 minus M1 by M1 plus M2 of G. Okay. So that's, you will get directly the acceleration of the system. Here external force, I said forces are two types depending upon system wise. System wise, I said external and internal. So in this example, what is the external force, what is the internal forces? Here, tension is the internal force here, and external force is gravitational force on this system. Ultimately, the blocks moves down. Okay. Now, what is from this formula? From this, by measuring this acceleration, suppose you calculate from this we can calculate acceleration due to gravity from this formula. So how do you calculate? G is equal to, by using this formula, A is equal to, G is equal to, what is M1 plus M2 by M2 minus M1 into A. So by using this formula, we can calculate acceleration due to gravity. This mission we can call it as Atwood mission. Atwood mission. Okay? Atwood mission. It is used to calculate acceleration due to gravity. By calculating acceleration. Okay? By knowing acceleration, we can calculate, by knowing masses m1 and m2, we can calculate acceleration due to gravity at a place. Okay? Then, I want a tension in this string. How do you calculate tension in this string? By substituting this value in this expression, either of the equations. You can substitute in equation 1 or in equation 2. That is your wish. You will get a tension in this string. Let us see how I will get this tension in this string. Now I will substitute in this equation. Okay? So I want a tension. T is equal to M1 minus T minus M1G is equal to M1A. So T I want M1 bring this side, M1G minus M1G bring this side plus M1A. So what is M1? You take it as common, G plus A. Okay? What is A? Instead of A, you substitute M2 minus M1 by M1 plus M2 of G. Okay? You take G is also common. M1G. 1 plus I want a tension in this string. Okay? M2 minus M1 by M1 plus M2. So this is, you take LCM, M1G. So what is LCM? M1 plus M2. So here M1 plus M2 into 1, M1 plus M2 plus M2 minus M1. Okay, minus M1 plus M1 get cancelled. M2 plus M2 get 2M2. So what is the tension in this string? What is the tension in this string? T is equal to 2M1 M2 G by M1 plus M2. Thus we got the tension in the string. Okay? This is the procedure, this is the way to calculate the tension in the string when you are using a single pulley. Okay? Now, I want how much force exerted by this support. I want next. I want force. I want FBD of pulley. You draw FBD of pulley. FBD of pulley. You treat pulley as a point mass like this. So what are the forces acting on it? T and T. So it is supporting. So this is supporting. Okay? Now what is tension in this? Supporting. So since the pulley is ideal, its mass is 0. So the net force acting on it is 0 from Newton's second law. Because F is equal to ma, since it is at rest or there is no mass, the force acting on the pulley is 0. So it is, if you draw FBD, it will become 2T. Since the block is at rest, the net upward force is equal to downward force. So what is the force exerted by the string on the pulley? How do you answer this question? Okay, so I want force exerted by the string on the pulley. Answer 2T. That is answer 2T. What is 2 into T? That is 4 M1 M2 by M1 plus M2 of G. Okay, that is force exerted by the string on the pulley. I want force exerted by the pulley on this support, on the roof. I want, because the pulley is attached to the roof. I want force exerted by the pulley on the roof. This is Newton's third law. The string exerts a force 2T on the pulley. The pulley in turn exerts a force 2T on this support. In turn, this support exerts a force 2T on the roof down. So the force exerted by the pulley on the roof is, answer is same, 2T. Answer is same, 2T. Okay, so this is Newton's third law. Clear? The force exerted by this support on the pulley is 2T. Force exerted by pulley on the support is 2T. Force exerted by the support on the pulley is 2T. Force exerted by this support on the roof is 2T. Force exerted by the roof on the support is 2T. From Newton's third law. For every action there is an equal and opposite reaction. So if you consider as a system, these internal forces, the tension is internal forces, though cancel with each other. Okay, so only external force will cause the motion to the system. That's most important. Okay, only external force can change the state of the motion. Okay, internal forces, it won't change the state of the motion. Take this.